on the crash course into discrete exterior calculus. We will continue with talking about the model and putting it into this setting. So the first thing we'll do is just to write down the definition of the lattice gauge theories more formally. And I will write pure in parentheses for reasons that we'll do later, maybe. So pure lattice gauge theory. On the set of cells, C1, with either gauge or structure group G, it depends a bit about on which paper you're looking. Is defined by or as a measure mu, and it will depend on n, that is the size of the box, and it will have one parameter beta, and it will assign each configuration, which will now be a form. We will think about it as a form because we can. And it will be defined by still e to the beta, but now instead of having this product of things, we will sum over a set of all packets. And packets, we're going to have two cells. And I will write something first that is strange, and then I will tell you why it makes sense. Rho of d sigma of t. And the idea here is that sigma is one form on B and taking values in the group G. So we have two differences from before. The first difference is that, and we need to divide by something, we need to normalize. So we're normalizing by, I guess, the sum over all sigma, and then the same thing. So we still have the normalizing thing, we still have the e to the beta and the sum of all the buckets. So what's different now is this, because before that was a product, and now it's this strange row thing, and we have a d sigma. So if you first remember what that was, if sigma is a one form, it assigns spins to all the edges, and it had this extra property that minus an edge had minus a spin. So d sigma p is then a two form, and that will we remember that d sigma of a packet is the same as sigma at the boundary of a packet, and it is a sum over all edges kind of in the boundary of a packet of sigma of e. So we're summing over things in the boundary, but previously we had a product of the boundary. So then the question is, why does the sum, or how do the sum magically become, this is supposed to be p and not p, how do the sum magically become a product? And the answer is in this row. And the reason we have a row here is that this is supposed to be math, and this is supposed to be a probability measure. So for that, this to be a probability measure, this needs to be a number. But I just said that I had a group. It needs to be a billion, because otherwise plus will not make sense. Or rather, if it's not a billion, we need to be much more careful when we write everything down. It's definitely doable, people do it, but now it's a billion. But you can easily come up with an abelian group that do not give you natural numbers, like Z2 would. But if you have, for example, Z3, like Z13, doesn't give you numbers anymore. And if you start looking at rotation groups such as SON, that would typically be a matrix. So you somehow need to map these group elements. Maybe we should even add a trace here. Let's add a trace. We need to somehow map group elements to numbers. The way to do that, to map group elements to numbers, is usually to use something called a representation of the group. So here, or above, row is a representation the group. So a representation will map group elements that are something abstract to something mathy. So for example, if the group is a group of all rotations of a three-dimensional sphere, for example, set of rotation, it's not numbers, it's rotations. That is a group, but it's not natural numbers. Then the representation will typically map that to a rotation matrix. So that's then the reason we need a trace. If the representation of the group is a matrix, we need that to somehow magically become a number, and the trace is usually how you do that. So that's kind of unpacking that, and then you could ask, like, how did the sum then become a product? Because now I told you that it's a representation, but if you don't work with representations every day, it's not obvious why that would help. And the properties of representation we will need is the following. So representation typically satisfies that if you have two group elements, G1 plus G2, then the whole point with representation is that the representation of the sum is the same as the product of the representations of the individual group elements. So representations naturally map sums to products. But that's why we need the representation. The other thing it typically does is if you have minus a group element, it will usually map it to the conjugate or conversion of that, a bit depending on what kind of representations you give out. But in the case that it's a complex number, the representation you can just take the conjugate. So that's the properties we will need from the representation. So representation maps from additive groups to essentially a multiplicative group. So in particular, if you look at rho of the sigma of P, which is what appeared there when I wrote it down, this would be rho of the sum of all the edges in the boundary of P, sigma of E. And now using this property of representation, we can kind of switch the sum to product. So this will be the same thing as the product over all edges in the boundary of P, rho of sigma of P. So there you have product and essentially the same product as we had before. And the special case which we'll care the most about is set 2. If G is set 2, which we naturally think about as 0 and 1, the natural representation of this group, to make an additive group into an interesting multiplicative group, would map this rho of 0 will be mapped to 1, so the neutral element in the additive group will be mapped to the neutral element of the multiplicative group. And rho of 1 will be minus 1. And if you do that, so for that reason, when we want to use discrete exterior calculus to define the model, we think of things as being 0, 1 valued, but when we then work with the model like in the formula, they will actually take values from 1 minus 1. And if you think about the Ising model, we usually have 1 minus 1 to start with. But here we actually start in the group and then kind of get 1 minus 1 as a consequence of the representation. But you can think of it both ways. But the good thing we think of about the set 2 is that you can use all these derivatives and stuff. And if you have a more complex spin group, this framework still works. If you use, like, write everything after the representation, things will be much more complicated. And then also, if the group is one-dimensional as said too, which I will use for the rest of this lecture, I think, then you can forget about the trace.
The trace is there because maybe you want to allow non-abelian groups?
Yeah, or you could have...
Non-abelian, do you need to do something more to modify?
If it's non-abelian, you need to worry a bit more, be a bit more careful in all stages, because then you might worry, like if you multiply, for example, around the edges in the boundary, you need to think about, does it matter in which order you multiply them, and here I don't. So you need to think, and it's kind of continuous like that in every step, and you need to be much more careful all the time about what you're doing.
Okay.
So the definition would look the same. You would just need to be much more careful with defining what you mean with the symbols. But otherwise it's the same. Any more questions? Yes.
So for row tree part, do you mean the adjoint of this row tree?
Yeah, so if I was mostly thinking about this as a complex number, but if it's a matrix, you need the complex conjugate of the matrix, something like that.
Normally it's inverse, but maybe you think about the unitary.
Yeah, I'm thinking about unitary representations. But I will mostly worry about set 2, so it doesn't really matter that much then. So there are two things now you could worry about a bit more before we stop thinking about set 2. The first one thing you could worry about if you're coming from matrices is, like, if this is supposed to be a probability measure, kind of an interesting one, you need two things. First, you need this to be real. You need the sum to be real. If you have ever taken a representation of a rotation group, and then taken the trace, you know it might not be real. So then you could worry, like, what happens then? The other thing you might worry about is that I'm summing over all the packets. So I'm summing over each packet and also the volume of each packet. So why is this sum not 0? Like, it would still be a probability measure, but then it would be uniform probability measures, so not that interesting. So that's two things one could think about. The reason this works, and that is not, neither of those things are a problem, is that if you think about rho of the sigma of p, that appears in the sum, and of the sigma of minus p appear in the sum. Both of them always appear because we always have two. So one of the worries would be that this would be 0, like one would be minus the other. And it's true that one is the minus the other before you take the representation. Because that was essentially the only thing we required from the one forms. So this is rho of minus the sigma of p. But what happens after the representation is not that the minus is moved out, it's that you get some kind of conjugate. So this is rho of the sigma of p plus rho of the sigma of p and some kind of conjugate. And the sum of a complex number, if we assume this is one-dimensional, plus the conjugate is exactly 2 times the real part of rho of the sigma of p. So that kind of solves both problems. It will not be 0 because these will not cancel, and it will in fact be real. So it's real exactly because we sum on both. If we wanted to sum over, say, only the positively oriented packets, because we thought that like one forms are kind of boring anyway because they have the same value essentially twice, then you would need to have the real part. But without that, you don't really need to have the real part. But if you don't need it because you sum on both. So the terms themselves do not need to be real, but when you sum on both, the sum is real. Like this doesn't have to be real, but this is kind of obviously.
So the assumption is unitarity?
Yeah. The unitary representation. Yeah, because otherwise you could do crazy things. So that is what we mean when we say that we study Lattice theories. We essentially mean that we study this measure. And now this is defined on a finite lattice again. And it's very natural to ask if that is necessary. And the answer is essentially no. for the same reasons as for the Ising model. So when you first define the Ising model, you usually first see this definition on a finite lattice, and then you can go to infinite lattice essentially in two ways. Either you can use a different definition and a completely different framework and actually get a model that's defined on the whole lattice. You can essentially use the same framework with some care here. But you don't get anything that's that more, like not much more interesting than the finite measure for large. And the other thing you can do, and that we will do later, is that as soon as you take expectations with respect to this finite measure, you have an observable, and we will talk about what kind of observables we want to have, and calculate the expectation of that observable, you can take the limit of that observable as n goes to infinity, and think about that. And there you have even nicer tools, because there's a paper by Genebra, which is extremely hard to read, so I don't really recommend reading it, but you can see people referencing it all over the place. And then they say that that's it's a standard consequence of the Genebra inequalities, that the limit of expectations exists and are translation invariant and everything you want. The paper is hard to read, but almost everyone refers to that paper to say that.
Sorry, could you list the paper when this happened?
What?
Could you just like say what the paper is?
So search for Genebra inequalities, and then
I just don't know what that word is. Could you write it?
okay, sorry.
The name of the author.
Yeah, the author. It's a hard to read paper, and it's hard because at the time I think Griffiths inequalities existed first, and he wanted to give a more general version of that, or prove it in the most general setting. And it turned out that doing it in the most general setting gave you a very general result, but the setting became very complicated, which is usually what happens. But it's used as a standard reference as soon as you take the limit and look at these equations. So this big N is not really a big problem, at least not now, and at least not more than it is for the Ising model. So the other thing that might be good to say something about was that, again, now lattice gauge theories, we think of the spins as being group valued, but I will from now on think of them as being Z2 valued. And we usually define it like that. So we separate the group elements and the representation of the group elements. So the spins are actually group valued, and then the representation of them maps them into plus minus 1. You can do exactly the same thing for the Ising model. People usually don't do that because discrete exterior calculus is perhaps a bit overkill for the Ising model. But you can do that if you like overkill. So in this, so the Ising model can be written in this language as well. Then you pick G to be Z2 with the same representation as there. And then the Ising model is given by, on a finite lattice, and let's use kappa now for the parameter, so this measure looks slightly different than the previous one. So you could think of this as being E to the kappa sum over all the edges as we have for the Ising model, and then the representation to get a number of the sigma of E, and then divided by the same, or some normalizing factor. So you could phrase it in exactly the same language. So if you start with something on the vertices, what the differential operator would do would be to look at the difference between the spins at the endpoints of its edge, and you could define it in exactly the same way. So seeing it like this kind of motivates this language, and also says that something about that these are actually exactly in the same family, because you can define them in exactly the same way. This was just defined starting on with 1 forms and having a weight and differentiating that, and these models start on 0 forms. So in the paper by Wegener, essentially this is the family he's looking at, but he says that, well, you can essentially start with any K cell in any dimension, and then defining your model in exactly the same way. So this is how we will define lattice gauge theory. So now we have the model, and this doesn't have any more. So the next thing I will want to do is to talk a bit about the properties of this model. Because now we have a model, but we need to discuss like what do we want to know about the model, what are the natural observables, what are people interested in, and so on. And before we can say what people are interested in, we need observables, and before we need observables, we need to kind of motivate them. Maybe we may erase this.
So beta is a non-negative number.
Non-negative number, yeah. And according to the paper by Wegener, there should be a phase transition. So there should be a magical special number somewhere in there. But it's a parameter. It's exactly as you have a parameter for the Ising model. It's a parameter. It could be big, it could be small. If it's small, the model should somehow be high temperature, whatever that means. And if it's large, it should somehow be low temperature. And hopefully something interesting happens somewhere in between.
So in this general setting you mentioned where you can start with any type of form,
Yeah.
what kind of symmetries do you get if you start with different types of form?
I will tell you that very soon. That's exactly the next. It's a very good question. Very good question. So the next thing I'm going to talk about, and we can blame Ellen for this, is symmetries in the model. Because it turns out that they are kind of important, and they will also describe or give you an explanation for why the model was so noisy. When we looked at it compared to the Ising model, where increasing the temperature seemed to like somehow give you some geometry of edges, whereas in this model that didn't really seem to happen. It's really annoying. So if someone opens the door kind of brutally now, there would be a lot of water on the floor. So don't do that. So when Wegener defined the model, he was looking for a model with a phase transition and local symmetries. The Ising model, in his meaning at least, did not have local symmetries because if you flip the value of any spin, like you cannot do that without changing the measure. Another name for local symmetries, which is usually used in the literature, is gauge transformations, and this kind of explains the word gauge. And the idea is the following. So we have a model defined like that. And we define it as a model on one form, but what we're really punishing is two form. It's not one form, it's two form. So to some extent, this is a model on two forms that can be, like that you can find by taking the derivative of a one form. That's also called closed two forms. So there's a name for that, but you can think of it essentially as a model on two forms which you can get by taking derivative of a one form. So now assume we have a lattice, and this works in any dimension where you can define the model, so the dimension has to be larger than 2. But here's a very small two-dimensional lattice. And assume we have some kind of form. So we have some spin value, the group value for each edge, each oriented edge. And it's a form, so the opposite edge has the opposite spin, or opposite group value. And now we have that sum over there. So the sum we're really interested in, and we can assume the group is Z2, so we can drop the trace, again, is the sum over rho of the sigma of P. And we sum over all the two cells of P. Now the local symmetry Wegener was talking about was the following. So pick any vertex, say this one. And what you will do, if the group is Z2, is, or in any case, add a group element, or flip the spin on each edge adjacent to that vertex. You can do that. So if we have a spin configuration to start with sigma, we can call this new spin configuration that is adds things close to that, something else. And the idea is that now if you try to calculate that for this new fancy spin configuration where I flick the spins adjacent to a vertex, for any packet you look at, it will either, such as this one, be adjacent to none of these flipped edges, or, so that will not change, like the weight coming from that packet will not change. And if you look here, it will have exactly 2 of those edges in there. So the weight will not change either, because in set 2, 1 plus 1 is 0. And if you have a more fancy group, the way to do it is you pick some vertex, and then you add something, the same thing to all positively oriented edges, and you add the opposite thing to all the negatively oriented edges to make sure it's a form. And then if you look at these things, these are not affected since they are not adjacent to this thing. But these will be affected, but if you look in the boundary of that packet, okay, so I should pick that for a second, it doesn't make sense. If you look in the boundary of this one, that one appears in positive orientation and that one appears with negative orientation, so then they will cancel for this reason. But the easiest way to see it would be for set 2, because then you have simply 1 plus 1 equal to 0. So formally, you would think about this like if V is a vertex and eta, which will be the orange thing, hence orange, is equal to V. So it's the one chain that is essentially equal to V. Then if we look at V, and instead of looking at sigma, we will add that thing. And I didn't really define that properly. So let's say not P sigma, but I did. That we add a differential of eta, and then you need to remember what that was. If eta was a 0 form, it had support on vertices, then d eta was the one form that had some support on everything in the boundary of the vertex. It will have support exactly there. Then this will be equal to d sigma. And the reason formally it will be equal to d sigma is that d is a linear operator because everything is linear. So this is equal to d sigma plus d in eta. And one of the things with this differential, which we didn't really talk about, but which extends from calculus, is that this thing, if you take d twice, it's always 0. So this is d sigma. So this is the local symmetry Wagner was talking about. You can do this here. You can do a local change and not affect the measure. Of course, you will affect the one form. This will give you a different one form, but it will give you exactly the same 2 form. So this is what's called a local symmetry. There are a lot of different edge configurations that have exactly the same weight. It's not one, it's in fact a lot of them, because you can pick any vertex and you can do this and get a new one. And if we look at Lattice, we have a lot of vertices. So you have like one symmetry like this for every vertex. And in fact, you could start with you could do this. For any 0 form, so omega 0, maybe down there, D and D, as long as you have a 0 form and add that to the 1 form, you would have that d of sigma plus d eta. So if eta is a 0 form, d eta is a 1 form that arises from a 0 form in that way. Would be d sigma. So this will only be a local symmetry if you pick like a very local one with a very narrow range definition, but you could do this for anyone. So in math or calculus math, this will be called change of variables. Like you do some change of local change in the edges, but the function or this weight would be the same. So in math, we call the local change of variable. In physics, it's called a gauge transformation. So that's the name. But the local symmetry you get if you look at only one lattice. This was the kind of local symmetry Wegener was kind of excited to find. And this works simply because you start with one forms. Because we started with one forms, so there is something of one dimension lower, like there are zero forms. Whereas for the Ising model, you start with zero forms, and then this also works simply because there are no -1 forms. But as soon as you do this with cells and start with cells of another dimension, that is just not zero. There are cells of a lower dimension, then you have these local symmetries. So in fact, all of Wegener's models, except for the Ising model, has local symmetries. But this is called gauge transformations. So it's good to be aware of this. And this is also why when we try to draw the edges of the model, it only looks noisy because like you somehow tell the model you dislike maquettes, but there are loads of different edge configurations that would have the same maquette weight because you could just do a gauge transformation and get another one. And hence you see no pattern with the edges.
So why do we bother thinking about it as a model on one forms?
Because we kind of like one forms. Because when you have one forms, you can just like pick anything, just pick anything from every edge and pick the opposite for the opposite. Like you immediately kind of see what you're doing. Whereas if I would do it for maquettes, I will need to define it on closed two forms. And then you need to wrap your head around what the closed two form is. Which I guess could be fine if you think about it for a week or two, but it's not fine if you just define it. So I guess that's the main reason. It's also more mathsy to think about it for closed forms, whereas like if you just wanted to define it, it's much easier to do in one form. I guess the same as for the Ising models. I guess you could ask any expert on the Ising model, why don't we just define the Ising model as a model of closed one forms? Why do we bother with the zero forms? Why do we define the Ising model on the vertices when it's really a model on closed one forms? And I guess the reason is it's simpler. It's easier to think about it. Although for the Ising model you still see something happening and here you don't. So this, as soon as you do this is usually called a gauge transformation. So if you look in the literature, you will see it quite a lot, especially if you look at the corresponding model but with an external field, because then it turns out that this is really important, and you're picking the correct gauge. And if you're interested in simulations, they're also extremely worried about picking the correct gauge, because then you could like think about like, well, but if I'm really interested in the paquette values and not the edge values, then I could maybe pick the gauge in a smart way so that I don't have that many edges there. So there are things called minimal gauge, for example, that when you do the change of variables so that you get as few edges as possible for a given set of paquettes. So that's the thing. But this is local symmetry, so that explains the name. It explains why the model is so noisy. Yeah. But again, it doesn't work for the Ising model. So now we know what the local symmetry is. Now we want to look at observables, because this is like one of the basic properties of models, but we still need observables because otherwise we have nothing to do. And before I tell you what the natural observable is, I'm going to do an example and also say something about the Ising model. So the first example we will do is just to try to calculate the expected value of something. Because the most natural thing to think of, and also as Ellen kind of said, that we define a model on edges. So the most natural thing to do and think of as an observable would be like, so what if now let's use D for expectation. I want to look at the expected spin at some edge. That would be very natural. Yeah, that would be really natural. Unfortunately, this will turn out to be very boring. And it will be very boring for two reasons. One kind of local reason as for the Ising model, and one, or a global reason as for the Ising model, and one local reason. So if we have no boundary conditions, and if you have studied the Ising model at any time, you know that Ising model has boundary conditions, usually. If we have free boundary condition, and you look at like the spin at the origin for the Ising model, it will be 0. So this will be 0 without boundary conditions here as well. But this will also be 0 for another reason, which has nothing to do with boundary conditions. Because you could imagine that if you have like plus boundary conditions or say something about the boundary, then this might be interesting. Because it is for the Ising model, it's very interesting for the Ising model. Say we try to calculate this. So what we said over here was that if I add like the differential of one form, I will get exactly the same measure. That was the whole point. So now I will try to pick this one form in a smart way. Because that should mean that this is exactly the same as the expectation of rho of sigma plus d eta of E. If I pick it in a smart way. Like it would hold anyway, because we said here that like adding that will not make a difference to the measure. They should have exactly the same measure, but these should kind of be the same. So now how will I choose this? Well, assume that this is my edge. So that's my edge. Let's call it E, because E is the name for edge. Now, I will not, like the measure will not change if I do a local gauge transformation. So then the question is like, is there a local gauge transformation I can do that will somehow enlighten us when we do this? And the one I will pick will be, I will flip the spin at all edges adjacent to one of the endpoints of E. That would change that. It would change the value of this edge, which you don't really care about, and that edge and that edge. But in particular, it will have to change the spin of E. So let's do that, and that will be called eta as before. So we call this eta. So now eta is that particular one, because I can pick any one. So if I do that, we can check what happens to our edge. And what happens, unfortunately, is exactly that it changes its sign. Like if because this thing switches the sign to anything adjacent to the vertex, and this edge got adjacent to the vertex. Or I don't want to change the sign, it will add 1 to it. So this edge afterwards will have spin minus, or rather it will have, okay, so I have to be more precise. Yeah, it will add 1 to it. So if the spin was sigma of E before, now remember this is a group element, the new spin will be this plus 1. Because that's what my gauge transform does. And now if the group is set to 2, which I'm assuming, adding 2, like if it was 0 before, it will now be 1, and if it was 1 before, it will now be 0. So this whole thing will be minus rho of sigma of E. But this is kind of bad, because now you have an expectation that's the same as minus the same expectation. And that will mean that the expectation of this thing, which we were interested in, has to be 0. And it will be 0 for any boundary conditions. Like you cannot solve this as you do for the Ising model. Because for the Ising model, an interesting question is like add plus boundary conditions and look at the spin at the origin and calculate the expected value. Now you can check that that will actually change the expectation at the origin, depending on what the parameter is in limit, but still it could change the spin at the origin. This shows that no matter what boundary conditions you have, the expectation of an edge will always be 0, which is a bit of a disappointment from a statistical mechanics point of view. But that's one consequence of these local symmetries. So as long as you have local symmetries, you cannot look at the expectation in a finite set. So as long as you just have some random spread out edges, it will be 0. It doesn't matter if you add 2, you will still have the same problem. Yes?
So that's for Z2. What happens for more general groups?
For more general groups, essentially you will have exactly the same thing. If you have a more general group, this gauge transformation, eta, so this is supposed to be a 0 form, so it's supposed to must assign a group element to each something. So let this be then the one where eta of the vertex still is some group element T. Your favorite one that is not. This cannot be like 0 because then it won't make a difference. So pick any group element. And then you could, what would happen up here is that instead of having +1, you would have plus some kind of group element. So you would track that all the way down and then you would have the same problem. So instead of -1, you would get some number on the unit circle, and then you would be in trouble. And in fact, it would be like you could do it for all the group elements, but you would get exactly the same thing. So this has nothing to do with set2. It was just like the only problem with this local thing, which ruins kind of everything. So you could do exactly the same thing. And I think this is in most papers on these models. They do some version of this just to show what happens. But you have exactly the same problem. So we cannot look at the expected value of the edge. And in fact, we not as for the Ising model that we cannot do it with boundary conditions. We can never look at the expectation of an edge because it will always be boring. So then the question is what can we actually look at if we do not look at edges? No, I really need to use the eraser again. Okay, so we cannot look at single edges. And I told you that you can kind of show that even if you have 2 edges, you will be in trouble because for the Ising model, the next natural thing would be to have if you don't look at the spin at the origin, you typically look at 2 spins at sides far apart. So you could ask, would that work here? To look at 2 edges far apart. But unfortunately, exactly the same argument shows that it fails. It will still be 0. You cannot do that. So neither of the observables that we have for the Ising model would work for gauge theory. So you need to do something else. And the thing you do is, it was already in the paper by Wegener, so he kind of figured it out without the physics motivation, but there is also physics motivation for it to do it. And we cannot look at edges. And as Ellen said before, this is kind of not an edge model. It's really kind of a package model on closed 2 forms. So the natural thing to do instead would be to look at the packets. So the main point is we cannot look at edges, we cannot look at pairs of edges, but that's bad. We can try to calculate the expectation of rho of d sigma of a packet. That is the probability that the packet is assigned some particular shape. That should work. And that should also work from the simulations you saw earlier this morning. That if you increase the parameter, the number of packets seems to decrease. So this is actually something that should be affected by the parameter. That's good. So that is what you can do. You can look at one single packet. And you can do that. People usually don't. And there are 2 reasons people usually don't. The first reason is that physicists want something slightly different. And the other reason is that this model, as I said before, has a phase transition. At least to my knowledge, you cannot see a phase transition by looking only at this thing. Or I haven't seen anyone do it. Am I wrong? So I don't think you have a phase transition for that. So you want something that has a phase transition because mathematicians kind of like phase transitions. And also physicists have some motivation for another one. So one plaquette works. And then we know for the Ising model that if you look at like spin on one plaquette, you can look at spin on 10 plaquettes. So what you usually do is that so we usually look at the expectation instead of not one plaquette, but many plaquettes at the same time, as you would say if you look at spin function, correlation function for the Ising model. And now we have language for that, because that's called chains. So we usually look at rho of the sigma of Q for some Q chain Q in it's a chain, it's not a form. Let's just remove that. And then more space. So some Q chain Q. That is for some kind of formal sum of plaquettes. So that would exactly, to some extent, generalize looking at a product of several things for the Ising model. The only difference is now we really need to look at plaquettes. We really cannot look at edges. So we usually look at that, but we don't think about it like that. Yes?
But is there a way, like heuristically, to understand why you see the phase transition when you take the formal sum, but not when you take just one, like just the expectation?
So it's more like I have never seen anyone look at the spin at one plaquette. So it's possible that it has a phase transition because the percolation version of this, at least to some extent, is plaquette percolation. And plaquette percolation is not as well studied as either vertex percolation or edge percolation, but it has several different phase transitions. So it might be that you could see it somehow on a plaquette. I just haven't seen anyone look at that. Not meaning that it's not doable. The other reason is that this is much closer related to what the physicist wants, because they have some heuristic explanation of what this should correspond to in physics. So that's usually why people started being interested in that, because if you want $1 million, for example, this is more important than 1%. But it might very well be that there is a phase transition we want to get as well. I just really don't know. But it's a good question. So we need a product of plaquettes. So now we're going to just quickly go back to the chains again. Because say we have a true form. So true form was a formal sum of plaquettes. The most natural ones is just like have one of each plaquette. Like have coefficients in 0 and 1. That's definitely the easiest one. Now we had Stokes' theorem. We had Stokes' theorem. Which we wrote on the board just before the break. We have d sigma of Q is same thing as sigma of partial Q. And if we have a sequence of plaquettes, like this, say we have 6 of them. And now I'm assuming that they are all positively oriented. It should have been bigger. Sorry, the backbone. They all have the same orientation. We saw before, very briefly, that if you put plaquettes next to each other with positive orientation, then in this plaquette, you will have that edge, and in the next by one, you will have one in the opposite direction. So if you pick something like this, the boundary will actually just be the things like outside. So the boundary, in this case, will actually be a loop. So what people usually do is that they start, so basically that says that like the expectation of a bunch of plaquettes should be non-zero, it should be interesting. But then by Stokes' theorem, that essentially means that if you start with a loop, then that should have an interesting expectation. So that means you can kind of look at edges, or the expectation of a set of edges, but they need to form a loop. And then you can do it. So the expectation of a product along a loop should have non-zero expectation. So the most important observable for that reason is when you pick a loop. So with a loop, when we say loop, we mean a one chain with coefficients that is usually in 0 and plus minus 1. So we don't go several laps around. You could do that, but not today. With no boundary. So a loop would usually have that, because if you have two edges next to each other, like the endpoints of them would cancel, but if you have a path, it would actually have two proper endpoints. So with a loop, we mean one chain with coefficients in there and no boundary. And usually, when you look at gauge theories, you make life even simpler and assume that the loop is a rectangle. So we will assume that the loop is a rectangle. And if we do that, then the observable, and usually this is denoted by W, gamma, which is rho of sigma of gamma. So remember, if gamma is a chain, this is simply the sum of the one form of the edges in gamma. That was the whole point with chains and one forms and stuff. Everything is linear. That observable is called a Wilson loop, after Wilson wrote the first physics paper on these models in 1975. There are other observables as well. There's, for example, one called a Polyakov observable, which is named after Polyakov, which is another physicist that kind of almost defined the same model at roughly the same time. But this is the one that's usually studied the most, at least in math. A Wilson loop. So you pick a loop which you like, and then you take the product. Yes?
So by loop, you also allow like multiple disjoint loops? There's no.
You could do both. So like, in particular, you could, for example, have two disjoint loops and look at the covariance between them. That's something you could do. So there is nothing in the definition up there that like forces the loop to be connected. It could be a collection of many, many loops. And in some cases that's useful. But again, the one that most people care about, and that's sufficient for you to win $1 million, is to look at the rectangle, which is good. So that's called a Wilson loop. So that's the most important observable in these models, the one most people care about. And that's the case even if you look at a more complicated group. This is what most people care about. Yeah.
Is it a theorem that when you look at the expectation of a path, then it's always zero unless it's a loop?
I can make it into a theorem for you if you want to, but essentially you would have exactly the same situation as here. You could even have like a very clear path starts here, And now, assume we've scaled things like crazy. So it has one edge here, but then it can loop for some time and do crazy things. That's the path. See? Starts here at that vertex. Since it's not closed, it has one vertex with odd degree, right? That's the whole thing with it being closed. Now I can do exactly the same argument up there. I pick this vertex. I do a local gauge transform, and that will show you the expectation is 0. So yes. So like you could trace it as a theorem, but it's exactly the same thing. If you add an external field, and I didn't tell you how to do that, but if you do that, then you can look at paths. But as long as you do not have an external field, it doesn't matter what boundary conditions you have, it will just be bad. Like you can look at paths. No matter how complicated you make them, as soon as you have one vertex with odd degree, it will be stable. But you can in principle look at very complicated loops. So what people are interested in the most are Wilson loops for large rectangles. And the math reason for looking at loops, again, is that edges will not work. So loop is kind of the next step you get from Stokes' theorem, because that corresponds to a collection of packets. But physicists are also interested in these loops for kind of a different reason, because this is like the math reason. This is the first thing that actually works, and someone tells you it has a phase transition, and then you kind of like it. But the physics reason is that this all comes from the standard model of physics, which is kind of important in physics, because it's the big bang bottom of everything. And they use Young-Mills, the continuous version of that, to describe that thing. And what the standard model of physics tells you, like the level on which it's at, is quarks. Like how quarks move through space and how much energy that will cost and how they behave in relationship to each other. And if you have a big rectangle, and now for this to be a meaningful physics theory, you need a more complicated group. So the simplest group you can have for this to be meaningful in physics, like really properly meaningful, is UR1. That is the group of rotations on the unit circle. Because if you do Young-Mills with UR1, you basically have a model for electromagnetism. That is UR1. So then you can describe electrons and stuff causing that. But you can do like everything works with some work here. If you then have a loop, a big one, they claim, and I haven't studied physics at all, so there are probably people in the room who can explain this better to you than I can. Basically, they describe it as having one quark here and an anti-quark here, moving them here. So this dimension is supposed to be space, and that dimension is supposed to be time. And then the Wilson loop, or the expectation of that, will tell you how much energy it costs to separate the quarks at that distance for that amount of time. That is what it's supposed to measure if you calculate the expectation. So it has that kind of interpretation, and then I guess if you were a physicist, you would say that, well, this really depends on which group you have, how you should interpret it, and so on. But it has some basic interpretation. So for them, the simplest way to move two quarks is to simply separate them and hold them still for some time, and that will represent a rectangular loop. So they come from it from that angle instead. But that's how they end up with rectangular loops. For a mathematician, it's more like, well, you have to have some loop. Rectangle is kind of the simplest one. You could pick a fancy one, but rectangle is the simplest loop you could pick. But for a physicist, it would have physical meaning to pick this one in particular. So the next thing I wanted to say something about was this, because that will kind of set us up for the rest of these lectures. So now I have an observable, and the only motivation for this observable so far is from physicists. Physicists claim it's reasonable, and if you want funding, it's good to claim that physicists are interested in what you're doing. That's kind of one reason. The other reason I've given you so far is just that, well, this is the simplest thing that might possibly work. So then the question is like, does it work? And in the lectures on Thursday, when these lectures continue, we'll talk about like how you prove something like this, or how you study this model. But for now, what I really want to say something about is this phase transition, or like how this actually do behave. So theorems. And this theorem should look a bit differently depending on which group you have. So for some groups, it will be slightly differently, but this is like general behavior. So there is beta, let's say beta 1 and beta 2, and they are somewhere in the range from 0 to infinity, which is that I'm claiming as little as possible. Such that if beta is smaller than beta 1, the beta is the parameter of the model, so it still has to be at least 0. It cannot be negative. But if it's smaller than beta 1, then the expectation, and we should have beta, of a large rectangle Wilson loop behaves kind of, and this is very sketchy what this tilde means. Some constant times e to the minus some other constant, and these most likely depend on beta, times the area of the loop. And if you define the rectangle loop as the boundary of a sum of a flat rectangle, then that will be that area. And 2, if beta is larger than beta 2, then this expectation should decay like some other constant. Let's call it c prime because then it's another c. E to the minus c prime times the perimeter of the loop. That is the number of edges in this boundary. So this should mean that in best case there is a phase transition between area law, which is this useful in the case like the area of the loop, and a regime where it decays like the perimeter of the loop. And if the loop is rectangular, the difference is quite large. Then this would be like the square of that. Yes?
Is that for g equals 2 or?
Yeah, so now it comes like, I'm very vague about the constant here. This is different for different groups, and it's different for different dimension, and also, in many cases, this is not properly known. So if, for the specific case you asked about, if the group is at least said 2, but I think more generally, and the dimension is 2, so that we look at the Z2 lattice. Then in fact we always have area law. So in that case, for these two, maybe we should even include infinity here to be safe. So then beta 1 is infinity, meaning that we always get area law. And that could also be the case for some groups. Yes?
But g equals 2, you mean the...
Yeah, sorry. G is said 2. Yeah. And the dimension is 2. Then we always get area law. If the group is still said 2, and D is 3, so that we're in dimension 3, then beta 1 is equal to beta 2, and they are actually some kind of interesting number that is known. And that's kind of a recent result. I think it's from a few years ago, like 2-3 years ago. Also by Duncan and Schweinhardt using a random positive representation. And if G is, you do this like once more, if G still said 2, and now this starts working for any finite group. So if, right, if G is finite, so that this is like discrete spin, or like the spins are discrete. And G is larger than or equal to 4. Then beta 1 and beta 2 are both kind of interesting numbers, but it's not known if they are the same. It's believed that they are the same, but it's not known even for set 2 that they are. So there might, in principle, be a third phase or like 10 different phases for these observable somewhere between area law and perimeter law, but it's not known. It's known that the worst possible decay is area law and that the best possible decay is perimeter law, but it's not known if this is sharp. So this kind of also tells you that these are not easy models just because they are discrete. Because already this is not known. And this is for finite groups. What people are really, really interested in, if you ask physicists or if you want $1 million, would be a continuous group. So this is kind of hard.
In 2 dimensions? Is there something?
In 2 dimensions, so I haven't tried doing it for, I mean, the argument for set 2D. So is there's theory, you know the answer? In 2 dimensions, if you have a more interesting gauge group, say a continuous one, you always get area law. You don't know. Given how the proof works in 2 dimensions, I would guess yes, because it basically only uses local gauge transformations, and then it kind of gives you that. But I'm not sure. The main point is this is still kind of not known. This is still complicated and hard and so on. The other thing one might say that kind of motivates this area to perimeter law thing, which is not, because this is a kind of strange phase transformation. So the ones you might have seen for the Ising model is that the expectation at the origin, for example, first is 0 for some time, but then it starts getting positive, which is a very nice thing because it's very clear how you distinguish between positive and 0 to some extent. You can see it using more complicated observables as well, but this is one way. Going from perimeter law to area law is kind of strange, not something you see in that many other models. However, one model which has exactly the same kind of phase vision is packet percolation. So if you do packet percolation on set something interesting, say set 3, set 4 or something, it has a very related observable with exactly the same type of phase transition. So that would also be one motivation for it. Apart from that, you might see in this model. But packet percolation has the same thing. So it appears in other places as well. The other thing one might say is that if you look at packet percolation, which is slightly more, maybe not studied more, because there's a lot of people working on gauge theories in different forms, but maybe easier to understand to some extent because it's percolation and you have no dependencies. Then it's known that you have several other phase transitions as well, not for the observable related to the Wilson loop, but for other observables. So it has several events that might occur with probability 0 or with super positive probability. So this model likely has more phase transitions as well, apart from this one. So this is not the only one, and most likely in higher dimensions, as for packet percolation, you have different phase transitions appearing at different times, because packet percolation has that. But this is the one you care about if you want $1 million. This is the one physicists care about. So therefore, this is the one that's most relevant here.
Is this a statement dependent on what n is, or is for n to infinity?
No, so I kind of dropped n, and I knew I did that. So what I mean here is that for this to hold, there is a tilde, meaning something needs to be large for this to kind of work. And the thing that needs to be large here is the loop. So you need to somehow let the size of the loop go to infinity for this to hold. So this holds for extremely large loops. Now, if the loop is extremely large, the lattice has to be larger because otherwise the loop wouldn't fit. So what you do is that we think of this as being the limit as n goes to infinity of the expectation on a finite lattice. And as we said before, this is not the same thing as defining the whole model on an infinite lattice at all, because we haven't done that. We're taking the limit of the expectation, although one might guess that if you could define the model on an infinite lattice, then the expectation would agree with this. But it makes sense to look at this due to this Geneva table. So if you look at any of the papers on lattice gated limits of these finite groups, you see at some point like this limit exists and is translation invariant due to the Geneva inequalities, which people write because there is no good theorem to make a reference to in that paper. So this exists and is translation invariant nice by the Geneva inequalities. But this is simply because we need a really, really big loop for this to kind of statically hold, and then for the big loop to fit into this box, you need the box to be even larger, and then it's better to just take the limit first on the size of the box. But this is the main phase transition, and the goal for Thursday is to try to give you some kind of motivation for why there should be a phase transition like this, because it's not at all obvious yet.
So are these mathematical results, or just so are these proof, this theory?
Yeah. So now this is extremely vague, right? Yeah. So I just said there is beta 1 and beta 2. I didn't say they are. So the main question in many of these theorems are they the same? So what you can usually prove, at least if you have a finite group, is that if, and not in 2 dimensions where you always have area law, but usually many of these finite group settings, like for the last one there, it's not too hard to prove that if beta is extremely large, you should have perimeter law. And if beta is extremely small, then you should have area law. So that you can usually do by, for small beta, you need to do first some version of what's called a high temperature expansion, which exists for the Ising model, to get the low temperature model, and then you can take beta extremely small to see that there should be area law. And yes, like you can do the same thing here, but then you prove it for, so in that sense you can prove the theorem, but for extreme values. So the hard thing would be to prove that these are actually the same, which I think is generally believed for these theories, but it's not really clear how to do that. So dimension 3 is really a kind of special case, and the reason this was doable was that this is a paquette model, and there is something called dual models, which you might have seen in the Ising model, where you can pick something that is dual to every cell. So for the Ising model, when we went from drawing like this model with edges to model with nice loops, what we did was that we replaced each edge in 2 dimensions with the dual of that edge, which would be the edge kind of going, crossing it, and you get something dual, and you might have seen that with the Ising model. That works very well in 2 dimensions, and then you could also think that each paquette is dual to a vertex, which you don't really care about for the Ising model because you're just happy to get the nice loops. But in 3 dimensions, things are more complicated because an edge is not dual to an edge anymore. But then each paquette is dual to the edge that kind of pierces the paquette in the opposite direction. So what happens then if you have a gauge theory, which is a model on plaquettes, is that in 3 dimensions that is dual to an edge model. An edge model is much more studied than paquette models. So that's why dimension 3 is easier. But I talked to them, I think, last week, and their proof really doesn't extend to 4 dimensions. Like they don't know how to extend it. It's not only that they didn't really care. It's more like they are heavily relying on the fact that packets are dual to edges in dimension 3, and otherwise it's not. So given how vague I stated this, it's known to be true. Like these are the behaviors you can get. So the interesting question is really like, what can you say about these parameters? For which groups are they the same? For which groups are they not 0 or infinity?
So are there any physical simulations
There are loads of physical simulations. Like if you look at HEPLAT at Archive, which is high energy physics, there are like 10 papers a day on versions of this. So like this is a big thing in physics, and what they're doing in physics is mostly simulations.
so there's no understanding between beta y and beta 2.
So if you ask physicists, they are the same for almost all models, I think. I don't think I've seen any model where they don't believe they are the same. But they have proven that using simulations, usually on a finite lattice, or like by definition on a finite lattice system simulation. So it's really, really, really not known. So in some models, maybe they know you know it for UO1. I need Christoph, and Christoph is not here.
In the second lecture.
Yeah.
Right.
I want him here now.
Yeah.
Just to say that I think for D equals 2, the result holds for all groups because of actual gauge fixing.
Yeah, I think that as well. So exactly that's what you're doing. So that's one particular form of gauge fixing, and then you should see it's true for all groups. I just haven't done it for non-abelian groups where you need to be more careful. But it sounds very.
I think it works, the same for all groups.
Yeah, it should work for the same group. But that's to say, dimension 2 is very special. So the proof you use in dimension 2, again, really, really doesn't work for higher dimensions. So you use a particular gauge. So this gauge transform was one that like you made a change of variables, and that gave you another set of edges. And sometimes, as you saw when you calculate the expected value of an edge, you can pick that in a smart way. Now, the smart way to do it in dimension 2. So here is a lattice, it's a 2-dimensional lattice. So you can really think about this as being 2-dimensional because I'm trying to make a 2-dimensional point. Here is lattice. We can assume we are looking at, say, this loop. I don't want it to be too large because then this will take forever. But this is a loop. So we thought before that sometimes when you want to calculate something, it's good to pick a good gauge. It's good to make a good change of variables first. And the change of variables we can essentially do is the one where we pick a vertex, like our favorite one, and then we switch the sign or switch the group element or add one to the group elements adjacent to it. So the way to do it in 2 dimensions is like start here, say, and now do the gauge transformation that will take all these 3 edges. That makes the spin on this edge 0. I can do that. That's basically the same as conditioning on that being 0, but it doesn't really change the measure because the gauge transformation. Then I want to make this edge 0. I can do that if I look at that vertex. I can pick the gauge transformation that makes this edge 0. It will affect these as well, but it will not affect the one that I already assumed to be 0. Then I can make this edge 0 by looking at this one. Then I can make this edge 0, and then it says, and then I can like do that whole axis 0. Then I could do the next line. I could even start by doing this thing 0, so let's just make that 0 as well. And then I can do this whole line 0. And then I could make everything here 0. And everything here 0. So I have like, that will give me the same value of the observable. And I can make them all 0 by gauge transformation, so it will not change anything. And now I want to calculate like the product of the spins along the loop. Now on these edges it's already 0, so that won't make anything. And in fact, since I have zeros all the way here, and these 2 edges do not really interact in any way because they have no common bucket, these rows are in fact independent. So the only thing you then need to care about is like what's the correlation between those two edges in this model. And now that expectation will not be 0 because now I fixed the gauge, I have zeros on these lines, so it will be something else. And it turns out that these two, this is a very, very sketchy proof. Sorry. So these lines will be independent. So if this has height t, if this is t and that is r, so the width is r by t. Like these are all, those are independent and I have t of them. And if I look at the expectation of that edge times that edge in this model where these are all 0, that will decay with the distance between them, exactly as you would usually see for say the Ising model. And in fact, on this strip, you only have some number of edges, and that's in fact a Markov chain. Like you can show that it's a regular Markov chain, like you saw in your first probability course, and you can kind of calculate correlations for a particular Markov chain. So this will essentially decay like E to some constant C R. This is the decay from the Markov chain. And then we have T independent lines, so we get T. And R times T is the area. So that is what you call referred to as axial gauge. You're kind of fixing everything on an axis. And it turns out that if you do that in dimension 2, everything kind of becomes independent, except for a number of Markov chains. So that will give you area law. So this is exactly, maybe we should have a C here. This is exactly E to the minus C times the area. So that gives you area law always in dimension 2. Problem is in dimension 3, like the reason you don't always get area law is that if you try to do this in dimension 3, you would see that you would not get independent strips anymore. So it wouldn't work. Like you could still pick a gauge so that a lot of the edges would be 0. That might help. Usually not, but in theory it could help. But the problem is that you cannot do it in a way to get completely independent things when this argument fails. But it works very nice in dimension 2. And this is also one of the reasons that if you want to look at gauge theories or lattice gauge theories, if you do dimension 2, that's a completely different story than all dimensions that are higher, because this is a very natural and very useful thing to do in dimension 2, and it fails completely as soon as that dimension is 3 and higher. So that's why you always have to. So one way to see why you might want to have area law could be that, well, it's kind of natural that some behavior from dimension 2 should survive if you increase the dimension. That might be a motivation for area law, but as you will see on Thursdays, there are kind of better motivations, both here and for plateau population. So we'll discuss them then. But I think this is a natural place to end.